Recording is rolling. It is Monday, October 20. So you guys are honors right here. We're going to do some Kahoots on circular motion. Well, I have a few Kahoots. One on circular motion and centrifugal force. You guys remember this? One of the recent labs that you guys did is you swing this canister around, this plate of canister was holding everything in place. Okay? And it turned out that the tension in the string, by the way, equal to this weight, okay, is equal to mv squared over r. So this mass times its speed squared divided by its radius curvature will tell you exactly the necessary tension. But as long as this is horizontal, it was pretty close to that. Okay. So you guys remember centrifugal force? Yeah. All right. Okay. So a lot of the questions might sort of be related to that. I do have one for gravitation and one for inverse square law, which is also part of universal gravitation. So yeah, let's kick this thing off. Oh, and then we've been doing this for 2 weeks. This topic, like circular motion, gravitation, all that. You know what? Do I have a gravitation here to show you guys? Where's scroll? Here we go. Okay. Another part of what we've been doing. So universal gravitation, when you're on the moon, okay, multiply them out together, divide by the distance between them squared, multiply universal gravity constant, boom, you got a force. Okay. Now, you put these two ideas together, put this and this together, and you can get orbits, right? If this gravity force is acting as a centrifugal force, you get orbits. All right, so we'll do as much as we can today. Let's flip over here. Oh yeah, look at you guys, ready to go. And the pen is on the board. It's not quite in. Yeah, let's get going. It's on circular motion. Circular motion. Which has greater linear speed on a merry-go-round? Linear speed. So if you point a radar gun at them, and they read different speeds, say miles per hour, meters per second. What's going to show us having the greatest speed? You could also call that tangential velocity. Could have said that term. The answer would be the same. Tangential velocity, linear velocity, linear speed. Uh, yeah, force near the outside. Force near the outside. Okay. Here, actually, I think I have enough to give you guys a demo with this. Okay. So, isn't that this right here? Here's your merry-go-round. And then here you go. Okay. So if there's a horse right in the middle, you would have zero linear speed. Okay, this guy has some speed, but this guy has like twice the speed. It's twice as far out. Okay, you guys know that too? So looking at it right there. All right, got points on the board. Oh yeah. Which has greater rotational speed, also called angular speed. This might be in radians per second. Wait. I'm going to shut this off at the 10-second mark. I'll put too much time on this. Greater angular speed, rotational speed. Just like rotating faster. Okay. Yeah, the same angular speed. Okay. So go back here. Okay, so this is the exact same scenario, but it's, the question's trying to go a little bit different. It's not like miles per hour, meters per second. No, it's saying like turns per time. Okay, so all these points make the same number of revolutions in the same time interval? Yeah, they sure do. Okay. You could quantify that in radians per second. That'd be the default unit for this class, radians per second. Yeah, they're all the same. They're all making the same turns per time. Got Cole, Dara, Anna, Bruce, Samuel, which is not a unit for rotational speed. Ooh. All right, pretty good. Yeah, because meters per second tells you how fast maybe you're going in a straight line. That would be a linear speed, right? Or it could be a tangential speed. Right? But all these other ones are turns per time. Like our default go-to is this one right here, radians per second, right? Radians per second. So I could say Greek letter omega is like so many radians per second. Right? But these other ones are same idea. Right, you guys ever heard of RPM? Isn't that what revolutions per minute radians? RPM. Okay. That's also a type of radiation speed. Hey guys, what about degrees per hour? Actually, I have a good example for that. How about the Earth? Yes. How long does it take for the Earth to rotate once, basically? 24 hours, right? And those could you call it 360 degrees? Okay. So in terms of degrees, 360. Okay. And then you said if I did that in 24 hours, wouldn't this give you the number of degrees that the Earth rotates every hour, right? Degrees per hour. Okay. What do you guys think that number is going to be? 15. Yeah. 3/2 times 10. Yeah, 15. Right. So if you ever see a globe, right, it has all of the lines of longitude marked around, right? Suppose there's like 24 of them, so you get like 24 time zones type. Okay. Yeah, approximately every 15 degrees, you get a new time zone. Okay. Every 15 degrees around the globe corresponds to the next hour. Yeah, that's it. All right, Dara, Cole, Anna, Samuel, Bruce. What is the direction of a force on that acts on clothes and the spin cycles of a washing machine? Yeah, inward. Okay, centripetal force always acts inward to hold you in a circle. Okay, okay, so this is a little different example, but it's the same type motion. Okay, guys, when I get the spinning, essentially like if I stop this, suppose this is coming around like this. Suppose it's coming around and I just brush stop. Because does Washington right here want to? He was coming around like this. Does he want to keep going in a straight line like that? Is that what you want to do? Yeah, right. And the other option would be, does he want to make a random 90-degree turn and fly straight away? No, that's not true. It must keep going straight line. So what's keeping him on a curved path is a what kind of force in this case? A frictional force. Yeah, frictional force. Right. Okay, second. And it's always holding him in. Like he's trying to go that way, but it's forcing him towards the center of the circle. Hence, it's holding him on that curved path. Okay. Now, if you replay the turntable example, what if this was like a a washing machine that was spinning around? Okay, washing machine. Okay. Could it be the walls, like the outer walls, are holding all your clothes in? Okay. And they would be pushing your clothes in like this, wouldn't they? Pushing your clothes in, preventing them from flying that way. Right? Yeah. So it would be a normal force, but it still acts towards the center of the circle. Okay? That's called centripetal force. Samuel, Gavin, Bruce, Dara, Anna, on fire. You whirl a can on a string. The string breaks. Oh, okay. Well, it can fly directly away, will fly a tangent to its circular path, towards you, or spiral away from you. What's correct? Yeah, tangent to a circular path. I do need a picture for that. I was thinking I had a picture for that question. I think there's a similar question to you. So let's say you're up in a helicopter looking straight down, and you see this guy right in the center, and he's got a string, and he's rolling this tin can. It's going around. See that looking straight down? He said, and let's say it's coming like this direction, got some instantaneous velocity that way. Okay? But of course, this is an motion; it's always being pulled in a circle. Okay? It's when it right at that snapshot right there, the string is breaks. Or maybe someone comes up with some scissors. It cuts the string. Okay? Okay, so the correct answer you guys just answered is the can flies off this way. Okay? It just keeps flying off in a straight line. Okay? One of the incorrect answers was, does it want to fly straight away that way? Right. There's actually no force vector, velocity vector. This is nothing, right? Other than if you're in the rotating frame of reference, you think you're being thrown that way, but from inertial frame of reference, this is the velocity vector right here. So that's the way that can actually goes. This one. Right. Boom. I got Dara, Cole, Gavin, Bruce, Anna. Ladybug rests on the bottom of that tin can being rolled around in a circle. The centripetal force this thing, on the bug is directly due to gravity, is from the can to the string, due to your hand. This one's maybe a little tricky. What's the best thing to it? Force on the ladybug. You're just focused on the ladybug. Oh, wait, yeah. And uh,
I got my foot on it.
Okay, yeah, that's a little tricky. That was a little tricky because these do all kind of yeah, like yeah, you use your hand to provide tension on the string, to provide force on the can. Now the can's directly acting on the ladybug. So if you're just focused on the ladybug, the best answer is the can acting on the ladybug. The ladybug can be like right here. Here's my ladybug. Right here. Doesn't the wall of the can provide maybe a normal force? Right. So that's pretty what I look for. Right, so, a little tricky. Yeah, that one's rigged. Yeah. All right.
No, I got it right, but then my thing disconnected. So
Sorry. No points for you. Olivia, Gavin, Gian, Anna, Bruce. Back on fire. Space. Oh, remember O'Neill's cylinder? The acceleration of the room. Let's call it G. Right. So we set this up for Earth gravity. And what if you went halfway? So out here at the surface, you feel okay. I feel 9.8 meters per second squared. I feel like I'm walking around Earth gravity. You climb a ladder. Get up to here. Sure. Ooh, what does the gravity field feel like here? It's not actual gravity. What does it feel like?
All right.
Yeah, it'd be half the value, half the G. So the poster that you guys saw that goes with that is this one right here. Okay, so here's your O'Neill cylinder. Okay, spin around. Okay. Now the target centripetal acceleration is probably 9.8 meters per second squared. Wouldn't that be good? So you feel like you're on Earth, right? Especially if it's pretty big. If it's a pretty big cylinder, maybe like a few kilometers in diameter. It might be kind of hard to tell if you're not in an actual gravity field. Okay, so we target 9.8 meters per second squared. Okay. And we can target that from knowing the radial size of the cylinder. Okay. And we can calculate how fast we have to spin it. So many radians per second. Actually, that'd be a pretty good question. How fast do you have to spin it to target? Okay. Do you think you could do that? Okay, so they give you 9.8 meters per second squared here. Supposed to give you this radius is like 3,000 meters or whatever. Okay. Could you calculate in radians per second how fast omega? Okay. Just divide over the r, take the square root. That's it. That's exactly how you did it. Okay. Right, so let's say we've done that. But now you got to climb this ladder. Now you get about to right here. Okay? So this radius is half of what it was before. But the omega is the same because you're on this giant like turntable basically where omega is the same everywhere. Like every point on this ladder has the same omega. Everybody's turning together, same radians per second. So half the radius is going to correspond to half the sort of artificial gravity field. You see it? Here's our artificial gravity field right here. Right? How about this? Great. What if you get right in the center of the ladder? Right in the center. What is your artificial gravity field?
None.
0. Yeah, because now this R goes to 0, so you don't feel any artificial gravity. You can push off, float off into space. Yeah. Let's hit that. Okay, you guys go with half G. All right, Gian, Ella, Dara, Bruce, Emma. Centrifugal forces and quote marks are an apparent reality to observers in a reference frame that is doing what? I almost never say that phrase. I say centripetal a lot. I almost never say centrifugal. Why? Something about apparent reality, huh?
Did you not?
If you're in a frame of reference that is... yeah, there you go, rotating. Right. Actually, a really good example is back to the Zodiac cylinder. So if there are two frames of reference, like 2 points of view, there's our point of view, like the camera point of view, or are we just kind of floating in space? Or we're all floating and we're watching this thing spin from our point of view. Right? And the other frame of reference is if you're actually walking around on the surface, you're in a rotating frame of reference. Isn't that true? Okay. So let's start with the inertial frame of reference. So as we're like third-party observers just watching this whole thing, we see Earth in the background, we see this kind of in front of us spinning. Okay. From our point of view, is there any forces actually throwing these people towards the outside?
Yeah.
Not at all. No. Right. What there is the walls providing a normal force that's holding them in, preventing them from see if this is spinning. Don't they? If the wall fell away, the floor from their point of view, when they actually fly, like these people would fly towards the air, right? They wouldn't fly straight away from the center. No. They actually fly tangent to their motion. Okay. but the spore is preventing them from doing that. That's the only actual force. The normal force is acting as a centripetal force. Now, let's switch frames of reference. What if you are these people? Maybe you have a blindfold on. You have no idea. Maybe you're even rotating. It feels to you like you're being thrown towards the outside. That's what centrifugal is. It's not an actual force, though. It's just an artifact of a centripetal force, is what it is. Right. All right, I got Ella, Gavin, Bruce, Dara, Anna. A person weighs less at the equator than at the poles. Why? Yeah, because the Earth is spinning. The Earth is spinning. Okay, actually, let's take sort of a pause from the. I'm going to do a little bit of math with you guys. Let's get the Earth going. Here's the Earth. Okay, equator. So, right, maybe North Pole, South Pole. Okay, and it's spinning west to east. So it's got so much. So it's spinning. Okay. Now, if you were at the surface of the Earth, well, the force that pulls you down is gravity. If you're on the equator, yes, gravity pulls you also towards the center. But as what the Earth was spinning really fast, could it possibly be that you could be thrown off the surface? Yeah, if it's going fast enough, and actually the whole planet would break up. But you get the idea. Okay. So I wonder what is the difference just due to the spin of the Earth? Do you think we can figure that out? Let's see if we can figure that out. I know gravity actual is the actual gravity field is we're going to go 9.8 meters per second squared. Okay. I know that the radius of the Earth. So this is all Earth is 6.38 times 10 to the 6 meters. So like 6 million meters about. And I know the angular velocity of the Earth. Well, you guys told me earlier, did you? Did you say it's one revolution every 24 hours? Is that what you guys told me? Okay. Okay. But guys, if I want to do any math with this, I don't need revolutions per hour. I need what for what? Radians per
Second.
Radians per second. Let's do it. Let's convert this to radians per second. All right, you guys ready to do this in your notes? So one revolution is how many radians? 2 pi? 2 pi radians? Okay. And then 1 hour is how many seconds? 3,600? Like that? So let's put all that together. And we'll get the angular velocity or like in terms of radians per second. So 2 pi divided by 24 and 3,600. Okay. So I'm looking at 0.0000727 rad per second. That's also called 7.27 times 10 to the negative what? 5. Aha, there you go. Yeah, 10 minus 5. Okay. Okay, so that's the number we'll actually plug into the math. Okay. So I'm thinking this guy right here. Let's put this guy on the equator. Okay. So free body diagram. There is really truly only one force on this guy. Okay, and that's his weight, mg. There's kind of a shortcut here. Well, sorry. There's two forces on this guy. There's his weight, mg, and there's a normal force, F sub n, like that. Okay. And up until last week, we always said, oh, well, those are the same. If he weighs 100 newtons, he has 100 newtons normal force. That puts him at rest. Okay. Now we're saying, well, that's not exactly true. He's on a curved surface that's rotating. Actually, I think the weight is a little more than the normal force. In fact, if he's spinning too fast, I bet the normal force goes down to 0 and he eventually flies off the surface. Right? If he's spinning too fast. Okay. So how much is the spinning effect? How much does it sort of alleviate his weight? Here, I'm going to throw in one number in the next one more. Okay, can I give him a mass of, say, 100 kilograms? Is that all right? He's like Santa Claus here. Like, I'm going to the equator. 100 kilograms. Okay. So what is his actual weight, this mg? Actually, you guys tell me. 100 times 9.8, what is that? 980 newtons. Okay, so that's how much he actually weighs. Okay. Now, if I say the centripetal force, guys, could centripetal force be m omega squared times r? Is that true? Right. Kind of like the O'Neill's up here. It's this one right here. I could also go b squared over r, but let's do omega squared times r because I already found omega here. Okay. Okay. So that is the difference between these two. So I'm going to say his weight down minus the normal force up, something like that. And his apparent weight is what the normal force is. So that's what we actually want. Okay. So what is the normal force? Add this, subtract that. Be mg minus m omega squared r. Okay. Here, I'm going to plug the rest of this in my calculator. Okay. So that's 980 newtons minus, okay, I'm going to put 100 kilograms here. Oops, 100 kilograms here times 0.000727 squared here times the radius of 6.38 10 to the 6. Okay. So that'd be, 3.37 Newton, or maybe 3.4 rounds too. Is that right? Okay. So subtract that, 980 minus 3.37. Okay. That's 976.63. Right. So basically 977. Right. Do you guys see that? 977. So he steps on a scale on the equator. The scale says you weigh 977 newtons. It's not exactly true. The Earth's gravity is actually pulling down with 980. You guys, 980 versus 977. Right. What if that is as a percentage? Let's see. Compared to 980. Okay. So, so 99.6%, something like that. And if you subtract that from 1, that tells you how much of your weight is alleviated at the equator due to their spin. Now, Florida, where it's some latitude value, if you kind of want to estimate, say, okay, well, it's probably like most of this, at our latitude. Okay. You could say that approximately 0.3% of your weight, 0.3% is alleviated due to the spin of the Earth. So if the Earth somehow like slowed to a stop and stopped spinning, your weight would increase by less than 0.5%. Okay, so it would go up a little bit. You probably wouldn't even be able to feel it. Okay, you wouldn't even notice. Yeah, a little bit it would go up. All right, back to here. We got Gian, Bruce, Gavin, Dara, Anna. The rotational speed of a space habitat increases. Let's see, the apparent weight of the people inside. The apparent weight. The faster it spins, everybody inside feels. Yeah, it feels heavier. Okay. So I'm looking at either one of these equations. You guys see, here's your angular velocity. This is increasing because it's spinning faster. Okay. Doesn't the apparent gravity here or your apparent weight here, either one, also have to increase? Okay. How about this? Here, let's do some proportions. You guys ready for some proportions? What if this is spinning at so many radians per second, and it speeds up to 3 times the angular speed? Guys, what if I throw a factor of 3 out omega? So you're spinning 3 times as fast. How many times heavier would you feel? 9. Exactly. 9. Because guys, it's a factor of 3 squared. So yeah, you feel 9 times as heavy. Yeah, you sure would. If it was spinning 3 times as fast, you'd feel 9 times as heavy. Pretty good. All right, got Nicholas, Gian, Gavin, Dara, Anna. Car travels in a circle with constant speed. The net force on the car is going around a circle. Yes, okay, so there's no tangential acceleration. But could there be a centripetal acceleration? Okay, that'd be different, right? Okay, tangential acceleration is like speeding up or slowing down. Centripetal acceleration lets you go around a curve. Yeah, because centripetal force is always directed towards the center of the circle. So if you're ever going around a curve, okay, because that's exactly this example right here, really. Okay, could this be a car making a left-hand turn? Right? Aren't all these cars making left-hand turns as they're going around? Okay, and isn't there a friction force that's allowing them to stay on that curved path? Okay, and that friction force is always pointed directly towards the center. If I made a free body diagram on well, either of these outer points, that frictional force would be pointing towards the center of the curve. That would be acting as the centrifugal force. All right, Nicholas, Gavin, Gion, Dara, Emma. In a space colony, what is the apparent gravity along the axis of rotation? Point to it. Axis of rotation. Okay. 10 more seconds. Yeah, where the arrow is pointing. Isn't that the axis of rotation right in the center? All right, 5 more seconds. Zero. Zero G. Okay, if you climb all the way to the center. Yeah, 0 G. Is that okay? All right. Oh, yeah. Nicholas, Gian, Gavin, Dara, Anna. Yeah. Conical pendulum. What force keeps the ball in its circular path? Ooh. Yeah, a little animation. How about that? It's keeping that ball along that peak circle. So is it the full tension, the vertical component of the tension, or the horizontal component of the tension? What do you think allows the ball to move along a horizontal circle? Horizontal circle. That should be the horizontal component of the tension. I have a conical pendulum here too. Try to dig this up. There we go. Here you go. It's this right here. Okay. So here's the full free body diagram. Weight down, tension at an angle. Boop, that's it. Okay. Now, this tension's doing sort of two things. Okay? It's holding up this mass up against its own weight, okay? But it's also pulling it in. You guys see it's like brown vector called net force. Okay? And actually, that is the horizontal component of the tension. It's this tension times sine of theta, okay, relative to the vertical. Right? All right, just like that. Horizontal, yeah. All right, Nicholas, Gian, Gavin, Dara, Anna. You ride a motorcycle in the opposite direction, opposite spin of the space colony, back to the O'Neill cylinder. So suppose the whole O'Neill cylinder is spinning clockwise, and you're riding counterclockwise. Let's take this to an extreme. What if it takes like a minute for the O'Neill cylinder to make one revolution, one rotation? And you're driving at sort of like an equal and opposite speed the other way. What are you doing relative to a nearby space station that's like floating over here? And therefore, how do you feel inside this O'Neill cylinder? You guys, 10 more seconds. 5. I think you would feel like, one winner.
What?
One winner. Here, see if I can explain this a little bit here. Where's O'Neill cylinder? Yeah, here's the O'Neill cylinder. So here's some guys walking around, right? Okay, I guess I got this one rotating the other way. But you guys get it, yeah. Okay. So if this rotating counterclockwise, and these people are say walking clockwise. Okay. It's what if they're walking clockwise as fast as this is turning counterclockwise? Okay. Wouldn't they be stationary relative to our point of view in our own station, just watching them? Okay. Guys, if they're just stationary, isn't it like they're not even moving? In fact, they might just kind of like push off and like float off into space themselves. Yeah, right? Right? They would feel totally weightless, wouldn't they? They'd feel totally weightless. Okay. Now that question was maybe a bit more variable. It's like, okay, just in general, what if you walk against the motion there? Hey, what if they turn around and walk in the same direction? Like if the whole cylinder is turning counterclockwise and they're also walking counterclockwise, how do you think they feel? A little bit what?
Heavy.
A little bit heavier. Yeah, a little bit heavier. Yeah, something like that. Now it whizzing around real fast. Yeah. All right. I got Nicholas, Gian, Gavin, Dara, Anna. Rotational speed of a wheel is defined as rotations per unit time. All right, 5 more seconds. I put so much time on these. True, yeah. So that could be revolutions per minute. That could be radians per second. Okay, those are common units. Some kind of rotation compared to time. Got Nicholas, Gian, Gavin, Dara, Anna. Space colony can be rotated so that Earth gravity is felt at the outer rim. Could you target 9.8 meters per second squared? Would you want to? Actually, right after this one, we'll do this calculation because this is a pretty good one. I like this question. This one might show up on the quiz, but I'll do it with you guys here real soon. Yeah, true. In fact, let's do this right now. Let's do this right now. So flip over here. So remember this. So you guys know the centripetal acceleration here, we're going to target 9.8 meters per second squared. And I have to give you the radius because different radial sizes, well, you have to spin either faster or slower to achieve that. So I'll give you guys AC target is 9.8 meters per second squared. I'll tell you that the radius of the Sonia cylinder, let's use 3,000 meters. I said that number earlier today, so I'll stick with that. Okay. So say I give you these. I'll call these given. Okay. So let's find the angular velocity. How fast do I have to rotate this? You guys get that? Okay. Okay. Here, you know what? I will how can I prop this up here? Does that all fit in the screen? Here. I'll solve it. You guys solve it. Let's see if we get the same number. I'll solve it off screen. And I'll show you guys my work after the fact. So I'm solving it right now. So I hope you guys are working too. We're all going to find out what is omega, how fast you have to spin this in radians per second. Square meters. All right, and calculator. Oops. What the heck? Let's get this back up here. There we go. It's all right, right? All right, I have the number on my calculator screen. Who else knows? Because who knows how fast I have to spin this? Okay, he's got a number.
Yes, 0.0571.
Aha, Gavin for the win. Oh, yeah. Okay, I'm just writing it down. Okay, right, so guys, I started with this expression right here. This centripetal acceleration can be the artificial gravity field. Okay, so we're going with that. Okay, so we're that right there. Okay. I plugged in my values. So 9.8 meters per second squared, we're targeting 3,000 meters radius. And I'm going to solve for this omega. So divide down the, well, actually, I plugged in the numbers first. Okay. So divide down the 3,000. Okay. And then take the square root. And that's it. Okay. And then I got 0.057. And that's radians per second, isn't it? Radians per second. Okay. Is that okay? That's how fast this works. So 0.057 radians every second is turning. You know what? I don't know. Maybe it's a little abstract because some of you guys haven't seen radians before this year. So let's turn this into a different question. Is how much time would it take to rotate once? Ooh, think you can figure that out? Okay. So let's pick up from here. And then here, I'll solve this here with you guys. How much time does it take for this, rotating this fast to rotate once? Okay. Could you do distance equals speed times time? Guys, distance equals speed times time. That's true, right? Okay. Is it also true in an angular sense? Theta equals omega times t. Is that true? Okay. And then could I solve for a t? Like how much time does it take to rotate once? You guys got that? Oh, but guys, rotate once. What is theta equal to? Huh? 2 pi. Yes. 2 pi in terms of radians. Okay. You could also said 1 revolution or 360 degrees, but 2 pi is the best answer because this is in terms of radians. That means we can do math with it. What number goes right here? 0.057. That's radians per second. Okay. So they'll give us time and guys, what unit will time come out to naturally? Will be hours, minutes, seconds. Yeah, it'll be seconds. So if I take 2 pi and divide by answer, I'm getting looks like 110 seconds it rounds to. 110 seconds. Is that almost 2 minutes? Is that what? Is that a minute 50 seconds? Okay, you guys got that? Okay. So if this O'Neill cylinder, find a picture, was like 3 kilometers radius or 6 kilometers diameter, if you like, it would take almost 2 minutes to rotate once, and then all these people inside would think that they were on Earth, or they would feel that way. Right. Boom, boom, boom. I got Cole, Gian, Gavin, Dara, Anna. The only reason that riders on a carnival ride don't fall out is because there's, well, okay. This is talking about a very specific, that's not a very good phrase question. Okay, okay. You got 10 more seconds. I'm gonna shut this one down. 5 more seconds. Okay, yeah, okay. So most guys picked the right answer there, but I need to give you guys a picture. Actually, a carnival ride could look kind of like this. Guys, what if you were in a carnival ride? I got this out of some Paul Hewitt materials. One of Paul Hewitt's videos talked about this. He's like, hey, actually, I may play this for you guys. Does this look familiar? What if you're in a carnival ride? It's going like this, and it's rotating around the central axis right here, right? And the floor drops out, and you're against the wall, right? Is that true? Right. Now, in that case, if you guys have been straight vertical, what force would actually be preventing you from falling down? Okay, so what's acting as the centripetal force? Friction. Friction. Yeah. You guys, what about this? What if you go in like really slippery clothes and wax paper and you're like, I'm gonna ride this ride, and you're all like slippery and it's like, I can't ride. Are you gonna fall straight out? Yeah, I'll fly off. Yeah. So better wear some clothes with some friction. That's what's holding you on that ride.
They got a dealer.
All right. A bug on a phonograph record will make more turns per minute if it moves towards the center. True or false? All right. 5 more seconds. Boom. False. Guys, I'm looking for false. See where it says turns per minute? Guys, turns per minute. Is that an angular speed? That's not a linear speed. That's an angular speed. Okay. Guys, here's a bug. It starts on the outside. Then he starts walking in towards the center. And then he gets here at some point. He gets here at some point. Guys, do all these three coins have the same turns per time?
Yep.
Yeah, they sure do. They're all making the same turns per time. Okay, you guys know a phonograph record looks like this, right? Got like a needle that goes in, like plays the whole album. Okay, there you go. Whoops, what just happened? Go here. Oh no, we're back. All right, Cole, Gian, Dara, Gavin, Anna. You whirl a can on a string. The tension in the string provides the centripetal force. Does that sound right?
Yeah.
All right, 5 seconds. Okay, yeah, basically yes. Just like your guys' last lab,
Yeah, it's
right? The tension in the string is holding the can in a circle. Something like that.
Isn't it one part of the tension though a little bit?
Huh?
Isn't it only one part of the tension force?
The horizontal component of the tension. Yeah, actually, that's technically true. Yeah, right.
Okay.
If you're going pretty fast and it's pretty close to horizontal, then yeah, right. You're right. If it was more like a conical pendulum, you're right. It would be the horizontal component. Yeah. All right. I think we're going for the win here. For the win, got Cole, Gian, Dara, Gavin, Anna. Who will win? Who will win? Ladybug on the inside of a spinning bike tire can experience a force that feels like gravity. 5 more seconds. True. Yeah, true. Right. Even if you threw it off a cliff and it's spinning, they're going to throw it outside. They think there's gravity, even though they're in free fall. Right. Hey, Gavin's here. I got Dara, Gavin, Emma. Oh yeah. Oh yeah. Okay. You know what? Let's do a quick Kahoot. I got inverse square law. We're gonna do a fast version. All right, you guys ready for a fast version? All right. All right, here we go. And give me a pin. Give me a pin. All right, we're back recording. Yeah, thank you everybody for hopping on real fast. We got about 7 minutes. We just have time. All right, you guys ready for Blitz Edition? All right, here we go. Blitz Edition. Pins on the board. Inverse square law. Actually, I think 8 of these are inverse square and 2 of them are not, but you guys figure it out. Radius increases by a factor of 2. By what factor does force change? Read this here. So, guys, if you double the distance, what happens to the force? If you double the distance, guess what's 1 over 2 squared? What's 1 divided by 2 squared? You guys get that? Yeah, 1/4. Oh, one winner! One winner! Because it's 1 over 2 squared. If they're getting further apart, isn't the force getting weaker? And it's inverse squared, so it's 1 over 2 squared. Who got them points? Talia! Oh, yeah! Yeah, knows what's going on. What if you go the other way? Guys, what if you cut the distance in half? Isn't it just the opposite? What's 1 divided by 1/2 squared? Huh. Well, I think 1/2 squared is like a quarter, isn't it? And then 1 divided by that? What's 1 divided by a quarter? Is the force getting stronger? Because you're getting closer? Force is getting stronger? Yeah, look at you guys go. Oh, yeah. Oh, yeah. Yeah, points. Okay, this one is not inverse square, but you guys get it there. What if you double this big mass? Double this big mass. And everything else is the same. So double this big mass. What happens to the force? Okay. Cut some of these a little short right here. Yeah, the overall force doubles. Okay, you double the m, the overall force doubles. Right, all else equal.
Oh wait, no, I'm thinking about the wrong thing.
All right, how about okay, again, this one's not inverse square either. What if you triple each of the masses? You triple this big M, and you also triple the little m. What happens to the force? What is triple? 9. Yeah. 3 times 3. Right. Okay. I think the rest of these are. Yeah. Okay. The rest of these are inverse squared. So what if you quadruple the distance? So this distance is times 4. Throw a factor of 4 in that r. It gets squared. Yes, that's 1 over what? Yeah, they got 1/16 of the force. Ooh, now it's getting to be a tiny force. 4 times further away. All right, how about what about the other way? What if you cut the distance into a quarter as it just before? Think the force is getting really, really strong? 1 divided by a quarter squared. It's like 1 over 1/16. Would that be like 16 times the force? Right? Yeah. Oh yeah. Got Dara, Anna, Cole, Bruce, Talia. How about you cut the distance into a third? What happens to the force? Nine. It's 1 divided by a third squared. That's 1 over 9, which is 9. Right. So the force is getting stronger. Guys, the force is getting stronger. They're getting closer together. Right. They get closer together, the force is stronger. Further away, weaker. Like here, they're getting further away by a factor of 3. We're increasing the distance by a factor of 3. I think the force is getting really weak now. Ooh. Right? So 3 times the distance, the force is, well, 1 over 3 squared. It's 1 over 3 squared. Oh. That's yeah, there you go. 1/9 of the force. Yeah. 9th of the force. I got Dara, Anna, Cole, Aaliyah, Bruce. Oh, is this? Aha. Okay, so on Earth, you weigh 500 newtons. How much do you weigh on a planet of the exact same mass, but half of Earth's radius? Okay, now you can still use the same formula. Okay, universal gravity constant the same. I guess mass is somehow the same. Your mass is the same. Okay? But this radius is half of what it was before. So we like pack down a planet. So you got a super dense planet. Okay. So 1 divided by, okay, I got a half squared down here, like a half squared factor. Guys, what is 1/2 squared? Oh, okay. Guys, wouldn't 1/2 squared be 1 over 4? But it's 1 divided by a 1 over 4. Isn't that times 4? And the original weight was 500 newtons. So it's 4 times 500. You guys get that? 4 times 500? Okay. I got one more that's pretty similar to that. And this is for the win. You guys ready for the win? Here we go. See figure. And suppose you weigh 900 newtons. How much do you weigh on a planet with the same mass, but 3 times Earth radius? But it's a giant puff planet, so it's not more massive, but it is larger. Okay, so guys, throw a factor of 3 here. What's 3 squared?
9.
9? But okay, and then it's 1 over that, so 1/9. Is what is 1/9 of 900 newtons? Another way of saying that is Yeah, if you had a really tall tower that was 2 times Earth's radius sitting on top of Earth's surface, and you walked to the top of the tower, you'd be 3 times further away from the center. The answer would be the same. Yeah, let's go to the podium with the bronze, Talia, the silver, Bruce, and the gold, Cole. All right, nice job, guys. I'll wrap that up today.